Hello students, welcome to the class. So today we will see the theory part 5 of the chapter Thermodynamics, where we will cover the section 5.3 of the NCERT. So this is the disclaimer. Now in this class our objective would be to see the experimental method for the determination of the internal energy change, which is represented here by delta U. Now we already know that we are covering the section 5.3 and in it we have the measurement of delta U and delta H. Now our objective is to specifically look at delta U. We will look at the delta H in the next session. So which is internal energy change. Apart from this, we will also look at a question which is in text question 5.6. So let us begin our discussion. Now the method which is used for the determination of the internal energy change is known as calorimetry. So it is a device. If I talk about that device, it is basically looking after the energy changes that are associated with a chemical or a physical process. Now this energy change is determined with the help of some state function, which is obviously our internal energy change and enthalpy change. So what are we doing? We are just quantifying this energy change, which is being measured in terms of the internal energy and the enthalpy. How does this calorimetry work? So it's a very simple setup. What you do, you carry out your reaction in a calorimeter. So there is a vessel which is known as calorimeter, and that vessel is immersed in a volume of a liquid. So this thing is simply done to reduce the amount of energy dissipation. So when you will look at the figure, when we will specifically move to the two types of calorimeter, there you will notice how the liquid is helping us to stop the dissipation of energy. One thing is very important in both the calorimeter that we will see. So that thing is the knownness of the heat capacity. So the liquid in which you are immersing your calorimeter, so for that liquid you must know its heat capacity. So it's very, very important. Why it is important? Of course, this term will be used for the determination of the delta H and delta U, that is your heat evolved in the following reaction. Now two things are there. The first thing I have mentioned earlier, so which is heat capacity. The second thing is the temperature change. So we will use a thermometer to measure the same. Now I said that we are going to measure two things, the internal energy change and the enthalpy change. Now these both are calculated at two different conditions. What are those conditions? First is at constant volume. So if you know the heat change at constant volume, then you are aware about the delta U as well, because both are equal. We know it. We have already seen the derivation as well. And for this kind of heat exchange in which the volume is constant, we carry out the reaction in a bomb calorimeter. So this is the first type. The second type is in which we keep the pressure constant, and that instrument is simply known as calorimeter. So two types of calorimeter are there. Again, I am repeating it. First one is at constant volume, which we call it as bomb calorimeter, and at constant pressure, which we call it as calorimeter. So our first objective is to calculate the delta U measurement, which is our today's objective. Now we have seen that for that we have to know the heat change at constant volume, and the apparatus which is used to calculate the same is a bomb calorimeter. So let us look at a diagram of bomb calorimeter. Now what you can observe here, you can see various parts of this bomb calorimeter. Let us start from the center. In the center, you can see a sample which is placed upon a vessel, or I would say a petal-like thing, and above your sample, we have a firing lead. What is the use of that firing lead? So that is used for combusting your sample. In that setup, what are we doing? We are supplying oxygen. Okay, so we are supplying oxygen, and this whole thing is kept under a steel bomb. So the first thing that we are looking at is a steel bomb. And that is the reason we call it as the bomb calorimeter. Now, if you look outside this bomb, what you will notice? You will notice a water bath. And in the water bath, we have two components. First is the stirrer and second is the thermometer. What is the use of the stirrer? So for that, you have to look upon your daily life experience. Suppose you are boiling a water. You're boiling water, right? Now, where the flame is touching your vessel, on that part, the water gets heated first. So this is being observed and this is very, very normal. Now, why it is happening? Because initially the heat is supplied to that part. Therefore, the heat, which is the water that is present closer to the flame, heated first. Now the question arises, why after certain time the whole water starts to boil? So its answer is very simple. Water is a good conductor of heat. So the heat that you have supplied at the bottom of the vessel, that is being spread throughout your water. Now, when you're doing a chemical reaction, you don't want such a condition in which the water that is present is only heated partially. You want heat to be quickly and uniformly distributed throughout the water. So what do? You stir it with the help of a stirrer. So basically it is rotating your water, and that rotation is allowing the heat that is dissipated in the combustion to spread uniformly. Got it? Now you can notice this phenomena also. So suppose you are pouring cold water in a normal water. What you will observe, that the top part of the water where you have poured the cold water will be lesser in temperature. Now stir the water with the help of your hand. After stirring it, you will observe that the whole water is now at the same temperature. There is no change in temperature throughout the water, right? Now that thing will eventually take place even you don't stir it, but if you want it quickly, you have to stir it with your hand, or in this case with the stirrer. Now the second component that we have is the thermometer. So what is this thermometer doing? It is observing the change that is taking place in your water bath in terms of temperature. Got it? Now, as I said you in the starter, that why are we keeping this whole set of bomb in a water vessel? Because we are avoiding the exchange of heat with the surrounding. And what we are doing, we are supplying that heat which is released during the combustion of the sample into your water bath. And in that water bath, the water's temperature is being measured through the thermometer. Okay, now what do we have? We have the temperature change, of course, and we also have the heat capacity of the water. So in this case, the liquid which we are using is your water. And I said you earlier that you are to be aware about the heat capacity. Got it? So till this point, we have some information about the system that we are dealing with. Now, if you move forward, what you will do? You will carry out the reaction. So the reaction is what? It is simply the combustion of the sample. Whenever this sample is burnt, as I said, so it will burn in the presence of pure dioxygen and no other gas, which is provided through the inlet. And after the combustion, the heat is involved, and this heat is transferred to the surrounding water, which is surrounding your bomb. And the temperature change in the water or the liquid is monitored with the thermometer. So this is our whole process. Now we have some information. What are those information? The information that we got is occurring at constant volume. So this was the most important part of your calorimeter, bomb calorimeter. And why the volume is constant? To look upon that, you should look at the bomb calorimeter. You will see that the bomb in which the reaction is being carried out, it is closed from the top. So the gases that are released, they are released in a fixed volume. So you can say that the volume is constant. Now, since the energy changes are occurring at a constant volume for the given reaction, therefore, no work will be done. Because work done is equals to minus P delta V. Okay. And since the change in volume is zero, therefore, your work done will be 0. Now, why are we taking this formula minus P external delta V? How are we sure that the work is irreversible? So I have discussed this thing. The natural process are always irreversible in nature. So pure reversible process is a hypothetical concept. Now, if you are calculating the QV, how you will calculate it? What will be the process? So it's very simple. We know the temperature change. We have already calculated it with the help of a thermometer. And we also know the heat capacity of the calorimeter or the liquid. You can use both the terms. So do not confuse it. You don't have to worry about it. It's very simple. I'm telling it again that the heat capacity of the calorimeter, or you can tell it as the heat capacity of the liquid. Both terms can be used in place of each other. Now, how do we calculate QV? Very simple. We know the heat capacity. We know the temperature change from the thermometer of the liquid. You can simply calculate the QV. Okay. Now the question arises, if you are calculating QV, right, for water, then you should take the heat capacity at constant volume, that is CV. But we are taking the simple heat capacity. So we are not implying any condition. We are simply saying that, okay, we can use the simple heat capacity of water rather than using the constant volume. What is the reason behind it? And do not take it as that the reaction is taking place at constant volume. Therefore, the heat capacity will be at constant volume. So this is a fixed quantity. We are taking it, right? And we are taking it as normal heat capacity and not any other specified heat capacity. The reason is that your water that you are dealing with is a liquid, okay? And for liquid, the heat capacity is equals to the heat capacity at constant volume is equals to the heat capacity at constant pressure, right? So this is only true for liquids. And why it is true? Because your liquid is not affected by the pressure, okay? So it is incompressible, and upon applying pressure, there is no change of volume also. Got it? Due to that reason, the heat capacity of the water is equals to the heat capacity of water at constant volume is equals to the heat capacity of water at constant pressure. And this is true for any other liquid or solid. I hope this part is clear to you. And remember, for gases, this will change. So we already know what is QV. It is the heat at constant volume, and C is the total heat capacity of your calorimeter. So in total heat capacity, we are including the system as well, the water, the bomb, and the container, all of this. Now you don't have to worry. If in case you are seeing it for the liquid only, then you can consider C for the liquid as well. And what is delta T? It is the observed temperature change. Now from this, you can calculate your QV very well from the given experiment. Now the question arises that we were interested in the internal energy change. Did we get it? Let's see. So the question would be, the answer would be yes, we got it. We got our internal energy change because we are doing the reaction at constant volume, and the heat change that we have calculated is the same. Now, since your work done is 0, and from the first law of thermodynamics, we know that delta U is equals to delta U is equals to Q plus W, and Q is equals to QV in this case, and work done is 0. Therefore, delta U is equals to simply QV. So we got our internal energy change. Now here is a question for you. What is the question? Question is saying that we are burning 1 gram of graphite in a bomb calorimeter. Okay. And we are doing it in the excess of oxygen at 298 Kelvin and at 1 atmospheric pressure. The equation for the same burning is given, or the combustion is given as C graphite reacting with oxygen to give us CO2. Now in this reaction, the temperature change is observed from 298 Kelvin to 299 Kelvin. Okay. And the heat capacity of the bomb calorimeter is given as 20.7 kilojoule per Kelvin. Then what you have to calculate? You have to calculate the enthalpy change for the combustion of graphite, and that at 298 Kelvin and 1 atm pressure. How you will do it? You already have the idea of bomb calorimeter, and You are also given with the heat capacity and temperature change. So I hope you can calculate the delta U from here. And the main question is that how you will calculate the delta H. So that is your interesting part. For that, you have to know a very known equation that we have discussed. And this equation is about the relation between delta H and delta U. So this thing, I'm leaving it up to you. I'm giving you time to solve it. Your time starts now. So your time is up. So let us look at the solution now. So if you have done it, well and good. If you have not done it, just be with me, and I hope you will get your solution understood very easily, right? So what is given in the question? We are given with the mass of graphite, which is 1 gram. So it's very, very important. The second thing is the initial temperature, which is 298 Kelvin. The third thing is the final temperature, which is 299 Kelvin. The heat capacity of the bomb calorimeter is also mentioned. It is given as 20.7 kilojoule per Kelvin. And the pressure is 1 atm. What we have to do? We have to calculate, first of all, the internal energy change. I have told you, for that, you have to know the temperature change, because the formula is given as QV is equals to C delta T. So delta T will be 299 Kelvin minus 298 Kelvin, which will be equals to 1 Kelvin. Now here is a very important point from your numericals point of view. What is that point? Suppose this temperature would be given in Celsius rather than the Kelvin. Okay, both of the initial and the final temperature are given in Celsius. Now in that case, if you calculate the temperature change, then you will not convert the final value of the temperature change into Kelvin. There is no sense in that. How do we know it? You can take a simple case, convert both of the temperatures to degree Celsius for the same question and calculate the temperature change. You will observe that the value is same in terms of degree Celsius also. So remember this thing. If you are calculating the temperature change, then you do not need to convert the units. Okay, the unit will be changed without changing the numerical value. So 1 Kelvin, if it is delta T, then 1 degree Celsius will also be your delta T. Both will have the same value. Okay, if you got it, good. So now we will put the value of the calorimeter heat capacity, which is 20.7 kilojoule per Kelvin, and the temperature. If you calculate it, you will get it as 20.7 kilojoules. So that's a very simple calculation. You just have to multiply it with unity. And in this calculation, the Kelvin will get cancelled out. So unit cancellation is very important in your numerical problem. You can see it. The units will get cancelled out because the Kelvin and Kelvin are present in the numerator and denominator. Now the question arises, the heat that we got is the heat related to the calorimeter. Okay, so this is very, very important. Again, I am repeating it. Since we have calculated the temperature change for the liquid, okay, so whatever the value that we will get for the heat change, that is with respect to your liquid or the bomb calorimeter. But you have to calculate the reactions enthalpy. Okay, so what you will do? You will just reverse the sign, because the heat that is released during the reaction will be the heat that will be absorbed by the liquid. Only one is getting the heat, so it will be in positive, which is plus 20.7 kilojoule, and the sample which is losing the heat will have a negative value of the same magnitude, which is minus 20.7 kilojoule. Got it? I hope this point is clear to you. Now you have the heat change for the reaction, and you have it at constant volume because the whole thing is being carried out in the bomb calorimeter. Next thing what we will do, we will just use it to calculate the delta U and then the enthalpy. Before that, one thing is very important. Although in this question, we don't have to calculate the enthalpy change in a certain unit, but you will use the normal convention or the standard convention, according to which the energy is always in term or the enthalpy change is always in terms of per mole. And here we are getting it for 1 gram. So to convert the 1 gram into mole is our first priority now. Molar mass of carbon is 12 because graphite is what? It is simply a electrop of carbon. So you will take the molar mass of carbon. And to convert it into moles, we will divide the mass by molar mass. Here the gram will get cancelled out and approximately you will get the value for moles of graphite as 0.08326 mole. You got your mole. So what do we have here? We have it for 1 gram. Okay. And we want to convert it for mole. So it's very simple. Just divide your Q reaction by moles of graphite. Got it? So if you do it, it will be minus 20.7 kilojoule divided by 0.08326 mole. Therefore, the final enthalpy change in terms of kilojoule per mole will be minus 248.6 kilojoule per mole. Now you got your delta H from here. Easy calculation. I hope this is clear to you. Now the question arises, how are we taking the Q reaction directly as delta H? What is the motive behind it? We know that we are conducting the reaction in a bomb calorimeter. So the Q reaction that we will get, that will be equals to the delta U and not the delta H. So here the tricky part is that if you look at the reaction, then on the reactant and the product side, we have no change of the number of moles, isn't it? You can see it very clearly that there is no change of number of moles. So in this case, your delta H will be equals to the delta U. Got it? Clear? So this is very, very important. I am directly putting it as delta H because this is a task for you. Just try to calculate the relation between the delta H and delta U, and you will find from this reaction that delta H is equals to the delta U because of the same number of gaseous moles on the reactant and product side. Therefore, the Q reaction that we got at constant volume can be equalized with the enthalpy change and further can be divided with the moles of graphite to get the enthalpy change in terms of kilojoule per mole. So it is written here that your delta Ng should be 0. Therefore, the delta H and delta U both are equals to minus 2.48 into 10 to the power 2 kilojoule per mole. Okay, clear? So this was all for the bomb calorimeter. In the next class, we will see the calorimeter in which we will try to determine the delta H. Because it is not necessary that in all the reactions, we will have the same number of gaseous molecules on both reactants and product side. So thank you for attending the session. I hope you enjoyed the lecture.